Now let me discuss about the path 1. When the system changes itself from A to B, you can see here this is the initial position and this is the final position. The system changes from A to B. By path 1, both pressure and volume changes. You can see here the pressure and volume changes. Pressure start decreasing and volume increases. Pressure decreases while volume increases. Work done by the system is positive. Last time also we discussed when volume increases, work done is positive. And that work done you can find out by area under the curve 1. By finding this area, you can find out the work done by the path 1. Means work done to change the state from initial to final. Now second path. You can see here this is second path. A to C and then C to B. So this is the second path. Now let me discuss about the second path. Now the second way to change the state from A to B is path 2. In this case, you can see here volume increases. So this is the initial volume is Vi now. Now up to C it is increases to Vf. Okay? From point A to C it increases at constant pressure. But the pressure A to C is what? Pressure is constant. The point A, C. In this region, pressure constant and volume increases. And volume is variable. Or we can say that increases. The pressure then decreases to Pf. So initial pressure is Pi and the final pressure is Pf. When we consider the final state B, the pressure corresponding to that is Pf. Pressure decreases. It means that C to B pressure decreases and volume remains constant. You can see here the volume is constant during this change. The system is now in the state B with its coordinate. You can see the coordinate Vf, comma Pf. The coordinate doesn't matter here. But here the path 2 is, so here A to C pressure is constant but the volume is increases from Vi to Vf. Now here C to B, when we are talking about C to B, in that volume is constant but pressure is decreases from Pi to Pf. So this is the second case. Now let me discuss the third path. Path number 3. You can see here this is the path 3. The work done in this process is represented by shaded end area under the curve 2. The third way, we are discussing about the third way. So this is not here. The third way to change the state from A to B is path 3 as shown in figure. In this case, you can see here. So this point to this point, the pressure decreases. Means pressure decreases from Pi to Pf. But the volume remains constant and the volume at that time is Vi. So volume remains same. Next, volume changes to Vf. Now here from this position to point B, the volume increases. Means volume changes and the pressure is constant. The work done in this process represented by shaded area. Shaded area. If you want to find out the work done, this shaded area gives us work done. Means you remember here one thing, area under this PV curve is a work done. Area under PV curve is a work done. It is easily noticeable that in the three cases we discussed, the amount of work done is not same. Means when we are a change from initial to final position by three paths. In all the three cases, work done is not same. It is different. Simple conclusion is here. The conclusion you have to remember here. So work done by system depends not only initial and final state but also on intermediate state, or it depends on path along which changes takes place. Now next article is heat added during a thermodynamic process. Now thermodynamic process, you know that many thermodynamic processes are there: isothermal, adiabatic, isobaric, isochloric. Now let's see here. Thermodynamic state of the system can be changed by adding heat. We already discussed in the previous. We can change the state by adding heat. Consider a thermodynamic system consisting of ideal gas. So we have to consider ideal gas confined to cylinder with movable, frictionless and massless piston. Means we are considering ideal situation. Suppose we want to change the initial volume Vi to the final volume Vf at constant temperature. At constant temperature means a isothermal process. There are two different ways in which this change in volume can be made. Now let me discuss both the ways here. So you can see here the diagram one, state 1, and this is state 2. So this is the initial volume Vi. Now this is the final volume Vf, and it is at constant temperature. You can see here we are heating the gas, but temperature must be constant here. Now the first is, you can see a figure. Figure shows the first method. In the figure you can see a first method. In this, gas is heated slowly. We are heating gas very slowly in controlled manner so that it expand. We already discussed previously also. When a gas expand, it cool. When gas compressed, its temperature increases. So here we are heating gas very slowly so that it expand at constant temperature. So when it expand, temperature start decreasing. Means temperature decreases. You know that we are heating it very slowly. So whatever the heat provided, it is used. It is used to change the volume, increase the volume, not to increase the temperature. That you remember. So it reaches the final volume Vf isothermally. The system absorbs a finite amount of heat during this process. I hope everyone understood the first way to reach a final state or to reach a final desired volume Vf without increasing temperature, means at constant temperature. At constant temperature means isothermally. Now, the second way. The second case we have to discuss, gas cylinder is now surrounded by insulating material. When gas cylinder is surrounded by insulating material, it is divided into two compartments. You can see here. So this is a gas cylinder which is insulated, and it is divided into two compartments by thin breakable partition. You can see this is a partition here. So you can see here the difference. In one partition you can see here gas, and in another partition is vacuum. Okay. The partition X filled with volume Vi, and it is a gas. The compartment Y is empty and its volume is Vi. Means the partition we divided into two equal part by thin breakable partition, so that total volume we can say that addition of these two volumes, or we can say instead of equal volumes we can write Vi dash and Vi also. So this Vi, and this is Vi dash. When we add these two, we get the final volume. Initial state is same in both the cases. The partition is now suddenly broken. You can see here when we broke the partition. This caused a sudden uncontrolled expansion of volume of gas. So it's the expansion of gas. Gas occupies the volume that was empty there before the partition. Okay? Before the partition is broken. The, means simply, so gas occupies the empty space. In this case, the gas has not done any work during its expansion because it has not pushed any piston or any other surface for its expansion. You know that I told you, but when we push the piston and compress the gas, then temperature increases. When we push the piston outward and gas expand, temperature decreases. But here, so we separated the gas and the vacuum by breakable partition. And when it is broken, the gas occupies the empty space, it expands. But during that expansion, work is not done. No work done during the expansion. And such expansion is called as free expansion. Means we attain here the final state Vf at constant temperature. We attain here final state at constant temperature. I hope everyone understood this. The intermediate states or the path during the change of state in the first and second case are different. But initial and final state are same. You can see here we learn the two cases. In the both the cases the path is different. But here initial and final states are same. So you can see here figure A and figure B represent two different ways. We already learned two different ways to take the state from system from initial to final state. This means we have two different paths connecting same initial and final state. In case of method 4.13, there is a exchange of heat. There is exchange of heat. You know that we heat the gas slowly and it expands. So exchange of heat is there. In second method, in second figure means what? We insulated this cylinder from the surrounding. There is no exchange of heat. And also the system does not do any work at all because there is no displacement of any piston or surface. The conclusion you have to remember here, heat transfer to system also depends on the path. Heat transfer to system also depends on the path. Now next article is classification of thermodynamic process. Thermodynamic state can be described by pressure, volume, temperature. These are the state variables. At present, we will restrict our description of thermodynamic system only to its pressure, volume and temperature. Listen, we are discussing only related to the pressure, volume and temperature. A process by which two or more of these variables can be changed is called as thermodynamic process or thermodynamic change. But in practice, for sake of measurement, any one of the state variable is held constant and other two are varied. This leads us to very useful way of classifying thermodynamic process. You remember one thing, one is variable and two are other two are constant. Oh sorry, one is variable, one variable is constant, means you know that PV is equal to RT. In that One we have to keep constant, means when it is isothermal, temperature is constant, and other two are variable. Okay, means changing, varied, and this leads a several thermodynamic process. Now let me discuss one by one here. The first one is reversible and irreversible process. What is reversible? What is irreversible? Reversible process is a change that can be traced in reverse direction. Reversible means it can be traced in reverse direction. Is the reversible? The path of a reversible thermodynamic process is same in the forward and reverse direction. The path must be same. You can see here. So this is the initial state and this is a final state B. Now, so initial state is changed to the final state B by, this is the first way. And again it changes B to A by the second way. You can see here the first and second way, both the ways are same. Means by same path it return. It retraces its path in reverse direction. That type of process is called as thermodynamic reversible process. Now pay attention here. Such changes are very slow. Reversible changes are very slow and there is no loss of any energy. No loss of energy in the process and the system is back to the initial state after it is taken along the reverse path. Reversible process are ideal process. It is ideal. A real thermodynamic process will always encounter some loss due to friction or some other due to dissipation of energy. Now you can see here example. In this example, here, the piston is changed from the state 1 to state 2. As we push the piston in, the gas compress. It reached from state 1 to state 2. As we release the force, again it come back to the state 1 by the same path. So this is the reversible. But here we are considering friction is no friction, no dissipation of energy. Listen. Now irreversible process. So irreversible process is a change that cannot be retraced in reverse direction. Means they can come to the initial position but by different path. Let I tell you simple example. Here you can see diagram here. This is initial position. This is the final position. Initial position changes to final by this path. This is the path 1. And again final to initial by path 2. You can see both the paths are different. So it is a irreversible. The path of irreversible thermodynamic process is not same. The path is not same, that you have to note here, in the forward and reverse direction. There is permanent. Why the path is not same? Because some permanent loss of energy is there from a system due to friction. Some energy is lost due to friction or other dissipative forces. You can see here the diagram. So from stage 1 to stage 2 we displace the piston, but when it is come back it is not able to reach the state 1 immediately. It come to the intermediate state here, this, and then it takes so longer time to reach the initial position. Or maybe if the frictional force is a more, then it may maintain a different position also. The change of state depends on path taken to change the, it depends on the path. Reversible process shows a hysteresis. This type of graph is called as hysteresis. Most real life thermodynamic process that we deal with are irreversible. So cause of irreversibility, you know that the thermodynamic system not goes back to original position by the same path. Then what is the cause? So there are mainly two reasons. So first one is lack of thermodynamic equilibrium. So most process such as a free expansion or an explosive chemical reaction take the system to non-equilibrium state. Means system is not in equilibrium. And the second one is dissipative effect, dissipation of energy. Most process involve friction, viscosity, electrical resistivity, or some other dissipative forces are there. And because of that, I mean, these are the causes of irreversibility. Now let me learn some assumption for discussion of thermodynamic process. The first assumption: majority of thermodynamic process we will discussing in the following section are reversible. Now pay attention. Whatever the process we are discussing, they are reversible. That is, they are quasi-static in nature. Quasi-static means what? They are taking so much longer time. They are extremely slow, and the system undergoes infinitesimally small, means infinite the change, means this is very small change basically. The system is therefore in thermodynamic equilibrium during all the changes, and we are considering thermodynamic equilibrium. So causes of irreversibility are lack of equilibrium. So we are considering, so thermodynamic equilibrium. The second assumption: the system involved in all process is an ideal gas enclosed in cylinder. So we are considering ideal gas which is in the cylinder, having movable piston, frictionless piston, and massless piston. Means ideal situations we are considering. Depending on requirement of the process, the wall of cylinder can be good thermal conductor. It depends. For isothermal processes, we require this. The walls of cylinder must be good thermal conductor or can be thermally insulated. Thermally insulated for what? Adiabatic process. Adiabatic means energy is not going out and not coming in. So in that case, it must be thermally insulated. Third one, the ideal gas equation is applicable to the system. Ideal gas equation is the PV is equal to RT. Now after that, we consider second process, thermodynamic process, and it is isothermal process. Isothermal means at constant temperature. The process in which change in pressure and volume takes place at constant temperature. You remember isothermal means temperature is constant. If temperature is constant means other two variables are changed. You know that PV is equal to RT. So R is already constant. Temperature is constant means pressure and volume changes. So pressure and volume, they are changing. For example, Melting of ice. You know that melting of ice. So you know that at 0 degrees Celsius ice is formed. When ice start melting, so temperature is not changed. It is 0 degrees Celsius only. Okay? Ice melt at constant temperature, which takes place at constant temperature here. And that is the isothermal process, melting of ice. Thermodynamics of isothermal process. The temperature of system remains constant in isothermal change, and Boyle's law can be applied. You know Boyle's law. P is inversely proportional to V. Therefore, the equation of state for isothermal change is given by PV is equal to constant. So this is the Boyle's law. Or you know that PV is equal to RT. This is the ideal gas equation. Then T is constant, R is already constant, so PV is equal to constant. So it means that PI VI is equal to PF VF. So PI is what? Initial pressure. VI is what? Initial volume is equal to PF VF. P is the pressure, F for final pressure multiplied by final volume. So consider isothermal expansion of ideal gas. The work done in that case is given by formula PdV. This is the work done. You can see here example of isothermal process. Pressure is inversely proportional to the volume. So when we heat the gas isothermally, it expands, means volume increases, but the temperature is constant. You can see here this a thermometer shows temperature, and this graph the relation between pressure and volume. You can see here the relation. They are inversely proportional, means pressure inversely proportional to the volume. The total work done in bringing out the piston from the initial volume Vi to the final volume Vf is given. So work done we can find out by integration of PdV, integration of P into dV. So between the limits Vi to Vf. You know that gas equation is PV is equal to nRT. By that gas equation we are written PV is equal to nRT by V. And then after substitution of that we get work done is given by this formula. And integration of this dV upon V within the limit after solving we get it is log of Vf divided by Vi. So we get this is the formula for work done. The third thermodynamic process is isobaric process. Isobaric means you can see here graph, and by graph you come to know that so here the pressure is constant. Isobaric process means at constant pressure. So for isobaric process, none of the quantity delta U, Q and W is zero. Not a single quantity. Delta U is the change in internal energy, Q is the heat supplied and W is the work done. Not a single quantity is zero here. Thermodynamics of isobaric process. Consider an ideal gas which is undergoing volume expansion at constant pressure. You can see in a diagram here. So we heat the gas, the temperature is increasing. This is a temperature meter. To maintain that pressure constant, so volume is increased slowly. So when volume is increased slowly, 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 that time you can see here the relation of the pressure and volume. So pressure is constant here. So if we consider that Vi is volume in the initial state of system, Ti temperature in the initial state of the system, Vf is the final volume, Tf is the final temperature, then we can apply here the thermodynamic first law. So work done in the expansion is given by work done, you know that formula of work done, P into dV. Or we can write the same work done by using a formula, P V is equal to nRT. The same formula, P into dV is equal to nR into dt. So here dV, it is dt. Instead of dt, we can use delta TL, so it's okay. Change in the internal energy of system. This is work done. Now similar manner, change in internal energy we can write. So this is the formula of the internal energy. N Cv into delta T. Cv is the specific heat at constant volume. And delta T is the change in temperature. By first law of thermodynamic, heat exchanged Q is given by. So you know that first law of thermodynamic, delta U is equal to Q minus W. So Q is equal to delta U plus W. So let me substitute here Q and W. So we get this formula for Q. But PdV, you can write N into R into delta T also. So we substitute, we get a different form of this equation. Q is equal to N into Cv into delta T plus NR delta T. Delta T you can take common, as well as N is a common. So after taking common factor, we get this equation. But you know that Cp minus Cv is R, Mayer's equation that we already learned. Cp minus Cv is R. So here we can write Cv plus R is Cp. So let me substitute. So we get Q is equal to N Cp into delta T. So Q is equal to N into Cp in a bracket. Delta T is the change in temperature. So final temperature minus initial temperature is the change in temperature. So we get this formula. The temperature of system changes in an isobaric process. Therefore, its internal energy also changes. And the internal energy, change in the internal energy formula, you already know that. This is the internal energy. Second conclusion is heat exchange is partially used for increasing the temperature and partially to do the work. You can see this. So Q is the heat. That heat supplied is utilized for what? Delta U means increase the internal energy and to do the work. The change in temperature of system depends on specific heat at constant pressure. Change in temperature depends on the specific heat. You know that specific heat relation and the change in temperature relation.